Welcome to Section 5.5 of the online video lecture series for intermediate algebra. I'm Dr. Scott Franklin. In this section, we're going to be looking at some special factoring formulas. Having already talked about pulling out the GCF, using factoring by grouping, and factoring trinomials by the reverse FOIL method, we are now ready to handle just a few more special cases that we can handle using formulas that are provided for us. So let's take a look at the first special factoring formula. The first special factoring formula we're going to cover is called the difference of squares. If we are given that a and b are real numbers or variables or maybe even algebraic expressions, then a squared minus b squared is equal to the following factored form. It is a plus b times the binomial a minus b. Now a quick check of FOIL, if you were to multiply out the right hand side, would show you that the outside and the inside terms cancel and you're left with a squared minus b squared. So what we're going to do is recognize the fact that anytime we have the difference of two squares, then it factors as the product of a sum and difference of those terms. Now let me show you what I mean with this example right here. We have x squared minus 64. There are two terms, and so our trinomial method won't work. Factoring by grouping we only use generally when there are four or more terms. And so we need a technique to handle this. Let's try our formula. The question is this the difference of two perfect squares? And what I always do when I'm working these problems is I write it down like this. I say, can I fill in the parentheses so that this statement is the same as the original problem? Is it something squared minus something squared? So I'll stick an x here because x squared is clearly x squared, right? Is there a number I can stick inside here that when I square it, I get 64? And clearly that number is 8. Now I recognize that I have this formula which matches this form here. If this were my A and this were my B. Now because of the formula, I can immediately factor and say this is A plus B times A minus B. Or in our case, x plus 8 times x minus 8. And that's it. That's all you have to do to factor when you see two perfect squares subtracted. Now please take note, it is difference of squares. There is no sum of squares formula. Let's try this one. Now at first glance it looks like the difference of squares, but I have a problem. I've got a 6 in each term, but 6 is not a perfect square. So can I use the formula? Well, yes, if you remember that the first step in any factoring problem is to factor out the greatest common factor. The GCF in this case is 6. I can pull a 6 out of both of those terms and I'm left with x squared minus y squared. Now there's my A, there's my B. It's the difference of two squares, so this is the same thing as 6 times x plus y times x minus y. Factoring the difference of squares is always the product of the sum and difference of those two numbers that are being squared. Let's try another one. 25x to the fourth minus 9y to the sixth. Okay, again, none of our techniques from the previous sections apply here because we have only two terms. The first question to ask is, can we factor out a common factor? There are no numbers that I can divide into 25 and 9, so no there, and x and y, there are no common variables to these two. So the next thing I ask is, can I write this as something squared minus something squared? Now let's try it out. Can I write 25 of something squared? Yes, it's 5 squared. What about x to the fourth? Can I stick an x to a power in here so that when I square it, I get x to the fourth? And the answer is yes. X squared works because remember, whenever you raise a power to a power, you multiply exponents. 2 times 2 is 4. So 5x squared, quantity squared, is the same thing as 25x to the 4th. What can you put inside here? I know I can put a 3, because 3 squared is 9. All right, y to what power, then squared, gives me 6? The answer is 3, because 3 times 2, right, when you raise power to power, you multiply, gives me 6. So here's my a, here's my b. It factors into a plus b, a minus b. So 5x squared plus 3y cubed times 5x squared minus 3y cubed. Multiply that out, you get the original problem just as a check, but that is our final answer on that example. Okay, let's look at the next one. Same thing, one more time. Let's try it again. Can I do this as something squared minus something squared? And clearly I can put an x squared here, because an x squared squared is x to the 4th. And I can put a 1 here, because 1 squared is 1. So according to my special factoring formula, this will be x squared plus 1 times x squared minus 1. Now I threw in a hint here whenever I said in this problem, as opposed to what I said in previous problems, I emphasized the fact that we need to factor this completely. Now, in every case, I technically need to factor completely, but I want you to now notice that I can actually go one more step. Look at this right here. Notice that that is something squared minus something squared again. Right? It's x squared minus 1 squared, isn't it? So I can actually factor this one further. Now the other one I can't. Because of the plus sign, this one does not factor. There's no formula for the sum of squares. But I can factor the second one further, x plus 1 times x minus 1, right? A plus b times a minus b. Now I look at those two and I can't factor them any further because they're nice linear terms. There are no squares left. The first one doesn't factor because it's a plus sign inside there, and there's nothing I can do to factor that. That means that one is completely factored. So the important thing to learn here is to check and make sure that after one step of factoring that you cannot factor again. If you can, you've got to take the next step. Let's do one more before we move on and look at the next factoring formula. In this problem, again, we are told to factor completely, but we're now given 4 terms: x cubed plus 3x squared minus 9x minus 27. Again, let me write down for you a hint I gave you earlier, but I did not write it down at the time. If you have 4 or more terms, always try grouping. That is your best shot for factoring these things. If it's 3 terms, then you try the reverse FOIL. If it's 2 terms, you try a formula. In this case, I have 4 terms, so let's group them together. Let's factor these and factor these by pulling out the greatest common factor. And remember, when you factor by grouping, you're looking for the GCF in each pair, and then you look for a GCF in the result of that. So first of all, what's the greatest common factor of x cubed plus 3x squared? That would be an x squared that I can pull out of both of them, and leaves me with an x plus 3. Now what can I pull out in common of a minus 9x and a minus 27? Remember that if the leading term is negative, you're going to pull out the negative as well. I do that here, and I can pull a 9 out of both of those, but I cannot pull an x out. Pulling a negative 9 out of minus 9x leaves me with positive x. And pulling a negative 9 out of negative 27 leaves me with a positive 3. Now notice that you have x plus 3 in both of these terms, so you can factor it out, which leaves behind an x squared minus 9. Again, remember to always check and see if you're done. X plus 3 will not factor further, but what about x squared minus 9? Notice that it is something squared minus something squared. In fact, it's an x and a 3, so I can use my difference of squares to see that this is x plus 3 times, now the sum of those would be x plus 3, times x minus 3, which is an acceptable answer, but notice because you have x plus 3 twice, I could rewrite that as x plus 3 squared times x minus 3, just by the fact that square means multiply times itself, so I can shorten my answer by writing it in this form. But either one of these would be a correct answer. Alright, factor by grouping when there's 4 or more terms. Always look to see if you cannot factor further, and if you can, you certainly need to do it. It turns out there are also formulas for factoring the sum and for factoring the difference of perfect cubes. We've done the difference of squares and noted that there is no formula for the sum of squares. But for cubes, if you have something that can be written as the perfect cube, meaning something raised to the third power, we can also factor those. For example, if you have the sum of 2 cubes, a cubed plus b cubed, that will factor in the following formula. Okay, my blank needs to be a little bit longer, but I'll squeeze it in. It will be a plus b, and then times a trinomial that doesn't factor any further. It's a trinomial that looks like this. It's a squared minus ab plus b squared. Now I challenge you to do this. If you were to multiply out the right hand side using your distribution technique for multiplying polynomials and simplify it completely, you do end up with a cubed plus b cubed. In fact, if you flick back to the section where we covered multiplying polynomials, you'll see an example just like this, only we went this direction. We went and multiplied it out and saw that we got the sum of cubes. Now in this case we're going to go the other direction. We're going to take something that is the sum of cubes and split it up into its 2 factors using this formula. We just have to identify what it is that's being cubed in the first and second place and plug those in for a and b into this formula. Similarly, there is a difference formula. That is, if I had a cubed minus b cubed, it looks very similar to this one. In fact, there are only 2 signs that change, but everything else looks the same. I change this from a plus to a minus, and I change the next one from a minus to a plus, and leave everything else the same. So consider this example right here. I want you to notice that you can't write it as the sum of squares because of the power 3 here, but I can do this as something cubed plus something cubed. And I do this again to identify what my a and my b are. So clearly it's x that's cubed to give me x cubed, and clearly it's 3 that I cubed to get 27. So again, there's my a, here's my b. I'm going to be using this formula right there. Okay, and it gives me a plus b, so x plus 3, times a squared, so that's x squared, minus a times b, x times 3, or 3x, plus b squared. Now b is the 3, so 3 squared is 9. If it's a number, go ahead and just multiply it out. And there it is. That is completely factored. Let's do the last one. So can we identify these as either perfect squares or perfect cubes? Because since the minus sign, this could possibly be a perfect square, and we could use our other formula for difference of squares. The problem is 125 is not a perfect square, neither is 64, and there are no common factors to pull out to make them into perfect squares. So the only choice then is to see, is it a perfect cube? And I'm going to go ahead and write it out and see if I can't get it to work. Can I cube some number and get 125? And just a quick check of the first few integers, and you'll see, yeah, 5 when cubed is 125. And can I raise x to a power so that when I multiply the powers, as raise a power to a power, I get 6? And clearly 2 works right there. So 5x squared, quantity cubed, is the 125x to the 6. Now, is there a number that when cubed gives me 64? And the answer is yes, it's 4. And also y squared would work because 2 times 3 gives me the 6. Now here's my a and here's my b. Let's write out plugging this into the formula. I have a minus b, I'll rewrite the formula right here, a squared plus ab plus b squared. That's what you get if you have a cubed minus b cubed. Okay, so thought bubble here. Remember that formula. So a minus b is 5x squared minus 4y squared. Okay, a squared, now I'm going to do this in two steps. A squared would mean take all of a, which is 5x squared, and square it. Plus a times b would be 5x squared for a and 4y squared for b. And then plus the b squared, which is 4y squared quantity squared. I just did this in two steps to make it a little bit easier to see where my numbers come from in the trinomial here. If I take 5x squared and squared, that's 5 squared, which is 25, and x squared squared, which is x to the 4th, plus 5 times 4 is 20, x squared, y squared, plus 4 squared is 16, y squared squared is y to the 4th. And there is your final factored form. Now you may say this is certainly not simplified, right? This up here is much simpler than this in the sense that it has fewer terms. But this could be considered simpler because everything down here has lower degree terms than this does. And in some circumstances, in some applications, it's nice to be able to have smaller degree terms. And in fact, that's what we're going to cover in the next section. The last section of the course is how we use factoring to help us solve equations that have polynomials in them. Remember that that's always the culmination of our chapters in college algebra, is to finally get to the chapter, the section that helps us solve equations with those types of functions. And that's what we're ready to do now. This is the end of section 5.2.